Hey folks, well as promised this time around we'll talk about activation records and get into some of the details that come along with this. Again, we're continuing on with this idea that we're trying to come up with some kind of an abstract representation of the subroutine calls that we're working with in a program. Alright, so the assumption is that each function, each subroutine has its own kind of local block of memory. So we need some way to represent that. So this block of memory is going to have all of the information necessary for a particular call to that function. So it's going to have the parameters that were passed to it. It might have space for the return value. It might have the return address in it. It's got space for the local variables. So this has got all of we'll think of this as just kind of one big abstract block. Again, how it actually turns out in code later is a different story, but in terms of our abstract representation, we'll just think of this as some kind of a record that's got all of the different pieces in it. So somewhere along the line, the compiler is going to have to figure out the layout for this. It's going to have to figure out how much space is allocated for each portion of it, right? How much space do I need for the parameters? How much space do I need for the local variables? And it has to think about come up with the offsets to each of them within the different pieces. So if I've got parameters x, y, and z, then within the space for the parameters, where's x, where's y, where's z. It has to make sure that it generates the actual code within the body of the function that actually sets up that space and cleans it up at the end. It's got to set up the code to actually access the individual parameters, to access the individual variables. Right? It has to go through and determine the layout, the structure for this, and generate the code to work with this. And the other thing that's going to crop up is if we're allowing these kind of nested lexical scopes, suppose I've got something like nested function declarations where I've got function f, and inside that I declare function g, and inside that I declare function h. Then h needs a way to be able to get at the activation record for g, and g needs to be able to get at the activation record for f, because if I declared variables in f, they've got to be visible to g and to h. And if I declared variables in g, they've got to be visible to h, because these things are nested one inside another in terms of our scopes. So this is something else that we're going to have to think about as we go through and construct our activation records. So we'll tend to think of our activation records as being kind of a chain. So the simple part of it is that, if we're taking a stack-based approach, then the call, oh my goodness, this should be a callee. Then the callee is always right above the caller, right? If function x calls function y, then x is stack frame is right below y's stack frame on the stack. So those ones are fairly obvious, where you've got this chain from the callee to the caller, and it's got one to the function that called it, and to the function that called it, and, or to the function, this sequence of calls. And again, you can think of this chain as typically being just our stack, where we're going through and saying, okay, x called y, called z, called whatever. But we've got this other issue with with our nested function declarations, for instance, where, again, if I have a case where here, let's say that f is defined inside function h. So taking a different example than I was just talking about. But so here we've got a function f that's declared inside a function h. So when I'm working inside f, I've got to be able to get at the variables that were declared in h. Right? H encloses f here. So in addition to being able to get from f to g, just by working our way down the stack, we want to be able to jump from f space to h's. And so it's going to be pretty common to have some kind of a reference, some kind of a pointer from f's activation record to h's. And then if h was declared inside some other function, it would have a pointer to, its parents, its lexical parents activation record, and again on up the line. So you might have these kind of multiple chains going on. You might have your stack going on and this other independent chain of lexical scopes. And of course, if we go to use a variable in f that's actually declared in h, we've got to find a way to traverse this pointer chain, get to the right activation record, and then get to the right spot in that activation record. So again, working off that example, so suppose our function h has some variable x that it's declared, and this variable x is at some offset of 8 from the start of h's space. Now, f, again, we're assuming is defined inside h, and f makes a reference to x. So the easiest way for, or at least one of the easiest ways for the compiler to refer to that x is to say, well, it's kind of one step down the chain, right? I want to follow this chain of pointers to my parent's lexical scope and use an offset of h from their space. So again, the same sort of idea. We want to go one layer up in our scoping and go at an offset of 8 from there. If I was going to refer to something that's actually in f's scope, then I'd just be using an offset of 0, right? Use my activation record. 1 is use my parent's activation record. 2 would be use effectively my grandparents' activation record, and just so on along this chain. Now, we could get the compiler to generate code to actually follow the chain of pointer references, follow, if it refers to an offset of 8 from my grandparents, then go through 2 pointers and go to an offset of 8 from there. Another possibility is to have, just to speed things up a little bit for deeper accesses, is to have a global array someplace where we keep this sort of collection of ancestor pointers. So I'm going to have this array, I'm just going to call it ARR for now, and in the 0 position I'll just have the pointer to the current activation record, and in position 1 I'll have a pointer to its parent's activation record, and in 2 I'll have a pointer to that one's parent's activation record. And when I make a new function call, or when I return from a function, I'll just update this global array with, correct the pointers for whichever one I'm in now. And so the idea is there's some overhead on the function calls and returns, but when I'm actually accessing individual elements within that function call, it's much quicker. Right? I'm not following a chain of pointers, I'm just doing one straight lookup in an array. So again, depending on the nature of the code you're producing, depending on the depth of the chains that you might get into, this may or may not be a useful process, right? If you know that there's hardly ever any significant nesting, then it might be simplest just to follow the pointer chain. Let's see, just a couple of other miscellaneous notes in terms of these activation records and the local code block. One of the things that can happen in our abstraction is that we can separate the declaration and initialization of our local variables from the code that actually goes on and uses it. So if I see a function definition that looks something like this, where I'm saying, okay, declare an integer variable y and assign a value of 3, and then go on and do something with it, and eventually return a value, then it might be the case that the compiler looks at this and says, okay, when I set up the stack frame for f, I'm going to set aside space for y, and I'm going to put an initial value of 3 in there. So that takes place as I'm setting up function f. So that means that when the function actually starts to run, the first statement it's actually going to execute is this one, right? The y is equal to whatever. So it might even be the case that I've got, maybe I do some interleaving here where I say, y is assigned 3, and then I've got a z is assigned 7 or something like that. So it might go through and have all of those things set up and initialized at the point of the function call, and then during execution it jumps to wherever the first actual sort of linear code statement is, if you like. So you might get this abstraction that separates those two kinds of activities, the setup and initialization from the stream of actions that take place once the execution actually begins. So just something to keep in the back of your mind. Just because the source code looks like these three things are happening in sequence, the int y equals 3 might not be, if you like, the first executable statement in the block of code for f. All right, one of the other things I wanted to get into a little bit was just this idea of where would these activation records actually wind up getting stored in memory? Our most common approach is this idea of just throw them all on the stack, right? For each of them, we'll have our current function's activation record is effectively that stack frame at the top of the stack. It calls a function, so it pushes a new stack frame on top of that. That calls a function, so it pushes the new stack frame on top of that. And as the function calls end, or as we return from them, we pop the space off the stack. So this kind of an approach is very effective, but it does assume that it's not possible for the callee to outlive the caller, right? The way things always have to work is the callee ends and returns control to the caller. There are other possibilities, right? If we want to support a kind of concurrency approach where one function can start another one, but then they can both exist afterwards, and either one of them can end first. And if just because the caller ends, it might not end the callee. Then we need a different approach. We can't just go from this idea of a stack, because we might have something in the middle ending first. So in this case, we might actually maintain some kind of a linked list of these things. And if one in the middle ends, then we kind of extract that one, remove that one element from the linked list and join the other, its predecessor and follower together. So in that case, we'd actually be looking at creating these activation records in the heap someplace and have some kind of a dynamic data structure to chain them together. All right, there are a couple of other optimizations that we should probably mention. If we've got a subroutine that doesn't actually call any other subroutines, then it doesn't really need to be on the stack, right? We know it's just going to exist for however long it runs for, and then it's going to end. So it's good. Effectively, we'd be putting it on the stack and then taking it off. One of the things that we could do instead is just have a fixed static activation record someplace off to the side, right, somewhere in our global space, that just exists for these leaf subroutines. And so when the subroutine gets called, we fill in that. When it ends, we extract that, and we don't need to go through all of our stack manipulations. So that is certainly a possibility. Another idea is if we've got an absolute fixed call sequence where X always calls Y, always calls Z, maybe Z is a leaf, then our compiler might be able to look at that and go, well, you know what? I don't really need to go through the overhead of these calls and returns. Maybe I can generate a single activation record for the three of them and optimize things a little bit that way. So there are certainly some possibilities. And again, we'll come back and look at this as we get into code generation and more on the optimization ideas later on. But these are things that we can start thinking about from our intermediate internal representations. All right, I want to sidetrack just a little bit next time around and look a little bit at heap management, since this is something else that our compiler is going to have to worry about. And then from there, we'll go on and look at some of the OO side of life. Here we've got subroutines down, but what would we do if we're trying to represent a hierarchy of classes and objects and inheritance and that kind of idea? So those are the places that we'll go through next and see where we get to.